You trust your feet. You have walked thousands of miles in your lifetime without ever thinking about it. Each step, a subconscious miracle of balance, muscle, and bone working in perfect concert. You take a step, you do not fall. The ground catches you. Now imagine a world where the ground still catches you, but slower. A world where each step launches you into a gentle arc that lasts seconds instead of a fraction of a heartbeat. A world where the sky offers no air to breathe. The sun scorches at over 200 degrees Fahrenheit, and the dust beneath your boots is made of microscopic glass shards that will shred your lungs if you inhale even a single particle. How far could you walk in this place? How long would it take to cross it? And here is the question nobody seems to want to answer. If you started walking right now, would you ever make it to the other side? There is something almost embarrassing about the question. How long to walk across the moon? It seems simple. Elementary school arithmetic. Distance divided by speed equals time. But the moon does not care about your arithmetic. The moon has been waiting for 4 billion years, utterly indifferent to the calculations of creatures that evolved on a world 384,400 kilometers away. It will wait 4 billion more. Your equations change nothing about its nature. Let us start with what we think we know. The moon has an equatorial circumference of 10,917 kilometers. That is roughly 6,786 miles. For comparison, the contiguous United States is about 4,500 kilometers wide. The moon's face, that pale circle you see hanging in the night sky, is roughly the same width as Australia or the European continent. If you are an average, healthy adult on Earth, you walk at about 5 kilometers per hour. Maybe a bit faster when you are late for something, a bit slower when you are just wandering. Divide the moon's circumference by that comfortable walking speed, and you get approximately 2,183 hours of continuous walking. That is 91 days, 3 months, a summer vacation of nothing but putting one foot in front of the other. But here is the problem. That calculation assumes you are walking on Earth. It assumes gravity is pulling you down at 9.8 meters per second squared. It assumes you have air to breathe, water to drink, food to eat, and ground that cooperates with the biomechanics of human locomotion. On the moon, you have none of these things. Not one. The moon offers you roughly 1/6 of Earth's gravity. Your body, which has spent millions of years evolving to move efficiently in a specific gravitational field, suddenly finds itself in an environment it was never designed for. The pendulum-like motion of walking, that elegant swing of your leg that conserves energy by trading potential and kinetic forces, stops working the way it should. Think about what walking actually is. On Earth, when you take a step, you essentially fall forward and catch yourself with your other leg. Your body operates like an inverted pendulum, with your center of mass arcing up and over your planted foot. At the top of that arc, you have maximum potential energy. As you swing down into your next step, that potential energy converts to kinetic energy. The exchange is remarkably efficient. Walking costs far less metabolic energy than it should, given how far you travel. But this elegant mechanism depends critically on gravity. The rate at which you swing, the height of your arc, the optimal speed at which energy exchange is most efficient. All of these scale with the gravitational acceleration. Reduce gravity to 1/6, and the math changes completely. The optimal walking speed on Earth is about 1.3 meters per second, or roughly 4.7 kilometers per hour. This is the speed at which the pendulum mechanics work best, where the exchange of potential and kinetic energy is most efficient. Theoretical calculations using what physicists call the Froude number, a dimensionless parameter that relates walking dynamics to gravity, predict that on the Moon, the optimal walking speed should be about 0.53 meters per second. That is only 1.9 kilometers per hour, slower than a leisurely stroll. But it gets more complicated. Researchers studying human locomotion in reduced gravity have discovered something fascinating. In 2012, a study published in the Journal of Biomechanics used predictive simulations to determine how humans would naturally move at different gravity levels. The researchers, led by Marco Ackermann at the University of São Paulo, found that at lunar gravity, the most energy-efficient gait is not walking at all. It is skipping. The Apollo astronauts discovered this intuitively. Watch the footage from any of the 6 lunar landings, and you will see grown men, decorated pilots, war heroes, scientists, bouncing across the surface like excited children. They were not being whimsical. Their bodies were instinctively seeking the most efficient way to move. Eugene Cernan, commander of Apollo 17 and the last human to walk on the Moon, reported that while skipping was preferred on level ground, hopping became the natural choice for downhill locomotion. Buzz Aldrin noted that the 1 foot in front of the other gait we use on Earth felt tiring on the Moon, with a rubbing sensation in the knee joints of his suit that made him feel a 1-mile trek would not be easy. This is where our simple arithmetic begins to crumble, because even setting aside the suits, the life support, the temperatures, and the radiation, the very act of walking on the Moon is fundamentally different from walking on Earth. Your muscles know how to walk on Earth. They do not know how to walk on the Moon. And the Moon has no patience for your learning curve. The Apollo astronauts moved slowly, painfully slowly, by Earth standards. During Apollo 15, researchers at NASA's Johnson Space Center tracked the walking speeds of astronauts David Scott and James Irwin as they explored the Hadley-Apennine region. Under similar conditions, their speeds improved over the course of the mission. During the first EVA, they averaged about 1.0 foot per second. By the second EVA, this increased to 1.5 feet per second. By the third, they reached 2.0 feet per second. These speeds translate to roughly 1.1, 1.6, and 2.2 kilometers per hour. Even at their fastest, the Apollo astronauts were moving at less than half the pace of a leisurely stroll on Earth. But these measurements came from short traverses while working around the lunar module or at geology stops. They were not sustained marches. The longest EVA distance on foot, without the lunar rover, was during Apollo 14, when Alan Shepard and Edgar Mitchell trekked 1,280 meters toward the rim of Cone Crater. The round trip took 4 hours and 34 minutes. Think about that. More than 4.5 hours to travel less than 3 kilometers total. On Earth, you could walk that distance in about 35 minutes without breaking a sweat. The culprit was not just the unusual gravity. It was the suits. The A7L spacesuits worn during Apollo were engineering miracles, but they were not designed for walking. They were designed to keep human beings alive in an environment that wanted them dead. 21 layers of materials, nylon, neoprene, mylar, Dacron, Kapton, Teflon, created a pressurized balloon around the astronaut's body. The suits weighed about 81 kilograms on Earth, though the lunar gravity reduced that to a mere 13.6 kilograms. But here's something that people often forget about reduced gravity. Weight changes, but mass does not. The suit still had the same inertia it would have on Earth. Moving it, starting it, stopping it, all of that still required the same force. And the suit fought back against every motion. John DeWitt, a senior biomechanist at NASA's Johnson Space Center, studied why Apollo astronauts hopped instead of walking. His conclusion was unambiguous. The astronauts did not hop because of low gravity. They hopped because their suits would not let them walk. The suits were not designed to optimize mobility, DeWitt explained in a 2014 study. They were designed to optimize life support. The suit designers were not concerned about making the legs move. They were concerned with oxygen, water, and cooling. As a result, the astronauts could not move their legs very much. Hopping was easier than walking. So let us recalculate our estimate. If an Apollo astronaut could sustain the maximum observed walking speed of about 2.2 kilometers per hour, which is generous given the fatigue and difficulty, circumnavigating the moon would take approximately 4,962 hours. That is 207 days, nearly 7 months of continuous motion. But the Apollo astronauts never came close to walking continuously. The longest any of them spent outside the lunar module during a single EVA was about 7.5 hours during Apollo 17. And even that was with frequent stops for experiments, sample collection, and driving the lunar rover. The moon is not a place where you walk for 7 months. It is a place where you survive for hours. Consider what it takes just to step outside on the lunar surface. The EVA, extravehicular activity, NASA's antiseptic term for walking on another world, requires hours of preparation. The astronaut must pre-breathe pure oxygen to purge nitrogen from their bloodstream, preventing the bends when the suit is pressurized. They must check and double-check every seal, every connection, every system. The suit's cooling system must be primed, its oxygen tanks verified, its communication links tested, and then they step out into a world that is trying to kill them in at least a dozen different ways simultaneously. There is no margin for error on the moon. A single puncture in the suit, from a sharp rock, a micrometeorite, a moment of carelessness, means death, not in hours, in minutes. The vacuum of space will not wait for rescue. Neil Armstrong and Buzz Aldrin spent just 2 hours and 31 minutes outside the lunar module during Apollo 11. They traversed a total distance of about 250 meters, less than the length of 3 football fields. They moved carefully, deliberately, knowing that every motion was being watched by 500 million people on Earth, and that their lives depended on making no mistakes. Armstrong later reported that NASA limited the first moonwalk's time and distance because there was no empirical proof of how much cooling water the astronauts' backpack life support systems would consume while working on the moon. They were operating at the bleeding edge of knowledge, with no room for experimentation. During those precious 151 minutes, Armstrong and Aldrin collected 21.55 kilograms of lunar samples, deployed scientific experiments, planted a flag, and took photographs that would become some of the most iconic images in human history. But they walked only 250 meters. By the time of Apollo 17, 3 years and 5 missions later, the astronauts had become more confident. Cernan and Schmidt spent 22 hours and 4 minutes outside over 3 separate EVAs. They drove the lunar rover 35.7 kilometers. They collected 110.5 kilograms of samples. They explored the Taurus-Littrow Valley in ways that would have seemed impossible to the Apollo 11 crew. But even this expanded capability was still measured in hours, not days, and certainly not in months. The NASA study from 2014 suggested something remarkable. If spacesuits were more flexible, astronauts might achieve walking speeds of 5 kilometers per hour, comparable to a brisk walk on Earth. This would cut the theoretical circumnavigation time to about 2,183 hours, or roughly 91 days of continuous walking. But continuous walking is a fantasy on the Moon. And here is why. Temperatures on the lunar surface swing between extremes that would kill an unprotected human in minutes. During the lunar day, which lasts about 14 Earth days, temperatures at the equator can reach 127 degrees Celsius, 260 degrees Fahrenheit. That is hotter than boiling water. Hot enough to cook you through your suit if the cooling systems failed. Then the sun sets, and for the next 14 Earth days, temperatures plunge to minus 173 degrees Celsius, minus 280 degrees Fahrenheit, colder than the surface of Mars, colder than anywhere on Earth has ever been recorded. In 2020, China's Chang'e 4 lander, carrying the lunar lander neutrons and dosimetry experiment, made the first direct measurements of radiation levels on the Moon's surface. The results confirmed what scientists had long suspected. Astronauts on the Moon receive radiation doses about 200 times higher than people on Earth's surface. The Diviner Lunar Radiometer on NASA's Lunar Reconnaissance Orbiter has mapped these temperature extremes with unprecedented precision, revealing that the lunar surface thermal environment is even more complex and extreme than previously understood. But at the Moon's poles, conditions are different, and in some ways, worse. Near the lunar South Pole, where NASA's Artemis program plans to land astronauts, mountains cast permanent shadows. Craters that have not seen sunlight in billions of years harbor temperatures that drop below minus 246 degrees Celsius. NASA's Lunar Reconnaissance Orbiter has measured temperatures in some permanently shadowed regions at minus 410 degrees Fahrenheit, colder than the surface of Pluto. These are not conditions for walking. These are conditions for dying. A lunar walker would need to carefully time their journey to avoid both the scorching heat of the lunar noon and the deadly cold of the 2-week night. They would need to traverse mostly during the brief windows around sunrise and sunset, when temperatures are merely survivable rather than immediately fatal. But even if you solve the temperature problem, there is the radiation. The Moon has no magnetic field worth mentioning, no atmosphere, nothing to stop the constant bombardment of galactic cosmic rays and solar radiation that pours through space. A study published in Science Advances in 2020 reported that astronauts would be exposed to about 60 microsieverts of radiation per hour while on the lunar surface in a spacesuit. Over a 7-month walk, that exposure would accumulate to levels that significantly increase lifetime cancer risk. And that is assuming no solar particle events occur during the journey. Between the Apollo 16 and 17 missions, the Sun erupted in a series of intense flares that would have caused radiation sickness, possibly death, for any astronaut caught on the lunar surface without shelter. The Moon does not want you to walk across it. This is not poetry. This is physics. Every aspect of the lunar environment conspires against human survival, as if the Moon were actively hostile to the presence of soft, warm, water-based organisms from Earth. Start with temperature. On Earth, we live within a remarkably narrow band of thermal conditions. The coldest permanently inhabited place on Earth, Oymyakon in Siberia, has recorded temperatures as low as minus 67.7 degrees Celsius. The hottest, Death Valley, has reached 56.7 degrees Celsius. That is a range of about 124 degrees. On the Moon, the temperature range at the equator is about 300 degrees Celsius. 300. The difference between noon and midnight is greater than the difference between the coldest and the hottest places on Earth combined, multiplied by more than 2. The Diviner Lunar Radiometer experiment aboard NASA's Lunar Reconnaissance Orbiter has been measuring lunar surface temperatures since 2009, compiling approximately 250 billion calibrated radiance measurements. The data reveal a thermal environment of extraordinary complexity. Maximum daytime temperatures at the equator reach 387 to 397 Kelvin, that is 114 to 124 degrees Celsius. Just before sunrise, temperatures plummet to about 95 Kelvin, minus 178 degrees Celsius. But these are averages. Local conditions can be far more extreme. Areas with abundant surface rocks, which have higher thermal inertia, stay warmer during the long lunar night, sometimes 50 Kelvin warmer than surrounding terrain. Shadows cast by boulders and crater walls create pockets of intense cold, even during the lunar day. The thermal environment is a patchwork of extremes. And then there is the timing. The lunar day is not like an Earth day. It lasts roughly 29.5 Earth days from sunrise to sunrise. That means about 2 weeks of continuous sunlight, followed by 2 weeks of continuous darkness. There is no quick relief from the heat, no brief respite from the cold. You bake for 14 days, then you freeze for 14 days. A walker crossing the Moon's equator would need to somehow navigate this thermal cycle. Walk only during the brief periods around sunrise and sunset when temperatures are merely survivable. Spend 2 weeks walking, then 2 weeks sheltering. The logistics become nightmarish. The polar regions offer different challenges. Because the Moon's axis is tilted only 1.54 degrees relative to its orbital plane compared to Earth's 23.4 degrees, the Sun never rises high in the polar sky. Some crater rims and mountain peaks receive almost continuous sunlight, while the floors of adjacent craters never see the Sun at all. These permanently shadowed regions are the coldest places in the inner solar system. The Lunar Reconnaissance Orbiter has measured temperatures in some PSRs at just 20 Kelvin, minus 253 degrees Celsius. That is colder than the surface of Pluto, cold enough that water ice deposited by comet impacts over billions of years has never sublimated away. Scientists believe these frigid craters may hold billions of tons of water ice, a resource that could be invaluable for future lunar explorers. But walking through them would be suicide. No spacesuit currently in development is designed to function at minus 253 degrees Celsius. Then there is the dust. Lunar regolith, the powdery layer of pulverized rock that covers the Moon's surface, is perhaps the most insidious hazard of all. It does not behave like Earth dust. It has not been weathered by wind or water. Every particle retains the razor-sharp edges created by billions of years of micrometeorite impacts. On Earth, dust particles are rounded by erosion, wind, water, and the constant grinding of particles against each other smooth away the sharp edges over time. But there is no wind on the Moon, no rain, no liquid water of any kind. The processes that round dust particles on Earth simply do not exist. Instead, the Moon has been subjected to hypervelocity impacts for 4 billion years. Micrometeorites strike the surface at speeds of 10 to 70 kilometers per second. At these velocities, the energy of impact vaporizes and melts rock, which then recondenses as tiny glass beads and jagged fragments. The result is regolith composed of angular particles with extremely high surface-to-volume ratios. The average grain size of lunar regolith is about 70 micrometers, roughly the diameter of a human hair. But the size distribution is broad. Some particles are as small as 0.01 micrometers, 100 times smaller than the wavelength of visible light. Others are centimeters across. The smallest particles are the most dangerous. Medical research has established that particles smaller than 10 micrometers can penetrate deep into the respiratory system. Particles smaller than 2.5 micrometers can reach the alveoli, the tiny air sacs where oxygen enters the bloodstream. Particles smaller than 0.1 micrometers can potentially cross from the lungs into the blood and travel throughout the body. Lunar dust contains substantial quantities of particles in all of these size ranges. And unlike Earth dust, lunar dust is chemically reactive. When fresh lunar regolith is exposed, it has not been oxidized. The iron in the minerals exists in its elemental and reduced states, not the oxidized forms common on Earth. When this reactive dust contacts moist tissues, the lungs, the eyes, the skin, it may trigger chemical reactions that release damaging free radicals. A study published in the journal GeoHealth in 2022 examined the potential toxicity of lunar dust to human cells. The researchers found that lunar dust simulants cause DNA damage, oxidative stress, and inflammatory responses in cultured human cells. The effects were comparable to, and in some cases worse than, those caused by crystalline silica, the mineral responsible for silicosis. But we cannot fully test the effects of authentic lunar dust on living humans. The Apollo samples are too precious and too limited. The simulants are approximations. The true health effects of long-term lunar dust exposure remain unknown. When the Apollo astronauts returned to their lunar modules after EVAs, they brought the dust with them. It coated everything. Harrison Schmitt, the only professional geologist to walk on the moon, developed what he called lunar hay fever, sneezing, throat soreness, eye irritation from exposure to the tiny regolith particles. In 2005, Schmitt declared that dust is the #1 environmental problem on the moon. And he was not exaggerating. The dust particles are small enough to penetrate deep into human lungs, some as small as 0.02 microns. Once there, they do not wash out. The moon's regolith contains over 50% silicon dioxide, the same compound that causes silicosis in miners and stonecutters on Earth. But lunar dust is worse. It has not been exposed to oxygen, so it remains chemically reactive. When it contacts the moist tissues of the lungs, it may trigger inflammatory responses that we cannot yet fully predict. A study published in 2022 in the journal MPJ Microgravity reviewed everything we know about lunar dust toxicity. The authors concluded that while Apollo astronauts reported only mild, short-lived respiratory symptoms, the spectrum of health effects associated with high-dose acute exposure or chronic low-dose exposure are not yet well understood. During a 7-month lunar traverse, an astronaut would be exposed to dust constantly. Every step would kick up particles that, in the moon's weak gravity, take far longer to settle than they would on Earth. The dust is electrostatically charged, so it clings to everything: suits, visors, equipment. It has abraded the joints of lunar rovers, obscured camera lenses, and infiltrated supposedly sealed compartments. Apollo suits showed visible damage after just a few days of exposure. A 7-month journey would shred them. The dust also has unusual electromagnetic properties. In the absence of atmosphere, the lunar surface is directly exposed to ultraviolet radiation and the solar wind, a stream of charged particles flowing outward from the sun. This bombardment gives the dust an electrostatic charge. During the lunar day, the sunward side of the dust particles becomes positively charged through the photoelectric effect. UV light knocks electrons off the surface. At the same time, the shadowed side may become negatively charged by collecting electrons from the solar wind. The result is particles with complex charge distributions that cling tenaciously to any surface they contact. Apollo astronauts tried to brush the dust off their suits before re-entering the lunar module. It did not work. The electrostatically charged particles stuck to the fabric, embedded themselves in the seams, invaded the joints of the suit. Nylon bristle brushes and vacuum cleaners provided only partial relief. Brian O'Brien, a physicist who designed some of the Apollo dust experiments, spent decades analyzing the behavior of lunar dust. His conclusion was unequivocal. Dust disturbed by rocket exhausts or kicked up by walking astronauts behaves differently from undisturbed surface dust. This collateral dust threatens thermal controls, operations, and the lifetimes of equipment left on the lunar surface. During the Apollo missions, dust caused the lunar modules to overheat during the lunar day. It obscured camera lenses and scientific instruments. It abraded the seals on sample containers, allowing Earth air to contaminate samples that scientists had carefully collected in vacuum. It clogged mechanisms and degraded virtually every system it touched. In 2014, China's U-2 rover, part of the Chang'e 3 mission, became immobilized on the lunar surface during its second day of operations. Chinese authorities attributed the failure to a control circuit malfunction in its driving unit. The most likely cause was dust infiltration. A walker crossing the moon would generate dust with every step. In the moon's reduced gravity, that dust would take far longer to settle than it would on Earth, if it settles at all. The charged particles might hover in a persistent cloud around the walker, coating their visor, infiltrating their suit's joints, clogging the filters of their life support system. There is no good solution to lunar dust. You cannot avoid it. You cannot clean it off completely. You can only minimize exposure and hope that your equipment holds together long enough to complete your mission. For a 7-month traverse, the dust would be a constant, omnipresent threat. Consider the logistics of such a walk. The life support systems on Apollo suits provided about 4 to 6 hours of consumables, oxygen, cooling water, carbon dioxide scrubbing. Later missions extended this to about 8 hours. The Artemis-era Axiom-U suits, being developed by Axiom Space, are designed for longer EVAs, but even they are not meant for continuous use over months. Let us do some rough mathematics. A human at rest consumes about 0.5 liters of oxygen per minute. Walking increases this to about 1 to 2 liters per minute, depending on intensity. For a conservative estimate, assume 1.5 liters per minute of walking, plus rest periods. Over a 7-month traverse, approximately 5,040 hours, with half that time spent walking and half resting or sleeping, oxygen consumption would be roughly walking 2,520 hours, takes 60 minutes x 1.5 liters, 226,800 liters of oxygen. Resting 2,520 hours x 60 minutes x 0.5 liters, 75,600 liters of oxygen. Total 300 to 400 liters of oxygen. Standard temperature and pressure, that is about 302 cubic meters of oxygen, compressed to the pressures used in spacecraft life support systems, typically around 6,000 psi. You would need oxygen tanks with a total volume of several hundred liters. But oxygen is only part of the equation. You also need water. The human body requires about 2 liters of drinking water per day, plus whatever water is needed for the suit's cooling system. Apollo suits used a sublimation cooling system that consumed water at a rate of about 0.3 liters per hour during active EVA. Over 2,520 hours of walking, that is 756 liters of cooling water alone. Add drinking water for 210 days, about 420 liters, and you are looking at over 1,000 liters of water for the journey. Water weighs 1 kilogram per liter. That is 1 metric ton of water. Then there is food. A human needs about 2,000 to 2,500 calories per day at rest. Walking increases this significantly. Marathon runners consume 5,000 or more calories on race day. For a lunar walker expending significant energy every day for 7 months, caloric needs might average 3,500 calories per day over 210 days, that is 735,000 calories. Freeze-dried space food provides roughly 2,000 to 3,000 calories per kilogram. You would need 250 to 370 kilograms of food. The numbers are becoming staggering. 1 metric ton of water, several hundred kilograms of food, hundreds of liters of oxygen, spare suit parts, batteries, communication equipment, emergency supplies, shelters for the 2-week lunar nights. You would need to carry or cache supplies along the route. Oxygen tanks, water, food, replacement suit components, batteries, communication equipment. A back-of-envelope calculation suggests that simply staying alive during a 7-month lunar traverse would require moving hundreds of kilograms of equipment, either carrying it on your back or depositing it at regular intervals along your route before you begin. But who would deposit those supplies, and how? The Apollo missions spent about $25 billion in 1960s dollars, over $150 billion in today's money, to put 12 people on the moon for a combined total of less than 3.5 days of surface time. The logistics of supporting a single person for 7 months of continuous travel would be staggering. And all of this assumes a straight line. It assumes flat terrain, which the moon emphatically does not have. The moon's surface is not a gentle plain. It is a scarred, cratered, mountainous hellscape that has been bombarded by impacts for over 4 billion years without any erosion to smooth the damage. Look at the moon through binoculars and you can see the craters from your backyard. Tycho, with its dramatic ray system spreading across the southern hemisphere. Copernicus, a 93-kilometer-wide impact scar in the ocean of storms. The great dark basins of Mare Imbrium, Mare Serenitatis, Mare Tranquillitatis. These are not ancient seas, as early astronomers believed, but vast plains of solidified lava that filled impact basins billions of years ago. But even the relatively smooth Maria are pocked with craters. Walk across Mare Tranquillitatis, where Apollo 11 landed, and you would encounter thousands of craters of every size. Some would be barely visible depressions you could step across. Others would be kilometer-wide bowls requiring significant detours. And the Maria are the easy parts. The lunar highlands, the bright, heavily cratered terrain that makes up most of the moon's surface, are far more challenging. Here, craters overlap craters. Ancient impacts were blasted by newer impacts, which were blasted by still newer impacts. The terrain is chaotic, jumbled, impossible to traverse in a straight line. The South Pole Aitken Basin alone, just one feature on the lunar far side, is 2,500 kilometers in diameter and up to 8.2 kilometers deep. It is the largest, deepest, and oldest impact basin on the Moon, and possibly in the entire solar system. Its rim is lined with mountains that reach summit elevations of 8,500 meters, higher than all but the tallest peaks on Earth. To put this in perspective, the basin is wider than the distance from New York to Los Angeles, and its floor lies deeper below its rim than Mount Everest rises above sea level. A walker could not simply walk around this obstacle. They would have to walk through it, descending and ascending slopes that would challenge mountaineers on Earth. While wearing a pressurized suit that limits mobility and weighs tens of kilograms, and South Pole Aitken is just one basin. The Moon has dozens of major impact basins, hundreds of thousands of craters larger than 1 kilometer, and countless millions of smaller craters. Every route across the lunar surface is an obstacle course. The slopes are particularly treacherous. Apollo astronauts found that terrain which looked gentle from a distance often proves steeper than expected when approached. The lack of atmospheric haze eliminated the visual cues we use on Earth to judge distance and slope. Mountains that looked nearby were actually kilometers away. Gentle rises turned out to be steep climbs. A study published in Acta Astronautica in 2024 examined the relationship between lunar terrain and astronaut performance during the Apollo missions. The researchers analyzed topographic data, astronaut reports, and audio and video recordings to understand how slopes affected EVA operations. They found that even moderate slopes, 5 to 10 degrees, significantly slowed astronaut movement and increased energy expenditure. A walker crossing the Moon would encounter slopes far steeper than this. Crater walls commonly have slopes of 20 to 30 degrees. Mountain flanks can exceed 45 degrees. These are not walking terrain on Earth, let alone on the Moon in a spacesuit. A walker crossing the Moon's equator would encounter the Maria, the dark, relatively flat plains of solidified basalt that early astronomers mistook for seas. But even the Maria are pocked with craters, and the highlands between them are worse. Mountains, valleys, boulder fields, slopes that Apollo astronauts found treacherous even over short distances. During Apollo 17, Eugene Cernan and Harrison Schmitt drove their lunar rover to Station 2 at Nansen Crater, at the foot of the South Massif. Their range from the lunar module reached 7.6 kilometers, the farthest any humans have ever traveled from the safety of a pressurizable spacecraft while on a planetary body. This remains the record, and it was set over 50 years ago. Since then, no human has walked on the Moon at all. To walk across the Moon would mean navigating terrain that has never been mapped at human scale. It would mean climbing slopes and descending into craters that could trap you forever. It would mean finding routes around obstacles that might require detours of hundreds of kilometers. The Apollo astronauts had difficulty perceiving distances on the Moon. Buzz Aldrin noted that the terrain varies a good bit relative to your ability to move over it. On Earth, you worry about 1 or 2 steps ahead. On the Moon, you have to keep a good eye out 4 or 5 steps ahead. The horizon on the Moon is only about 2.4 kilometers away, far closer than on Earth due to the Moon's smaller radius. This creates an intimate but disorienting sense of enclosure, as if the world is folding in on itself. Judging the size and distance of craters and boulders becomes nearly impossible without familiar reference points. You could walk into a crater that looks shallow and find yourself trapped at the bottom, unable to climb out in your rigid suit. You could misjudge a boulder field and find your suit torn by the jagged, unweathered rocks. You could simply get lost without landmarks or GPS on a world where every grey plane looks like every other grey plane. Navigation on the moon presents unique challenges. On Earth, we take for granted our ability to orient ourselves. The sun rises in the east and sets in the west. The stars wheel overhead in predictable patterns. Landmarks, mountains, rivers, cities provide reference points. On the moon, there are no roads, no signposts, no trails. The sun moves across the sky so slowly that it is useless for rapid orientation. The stars are always visible, even during the lunar day. The lack of atmosphere means the sky never brightens to blue. But using stars for navigation requires equipment and training. The Apollo astronauts relied primarily on recognizing landmarks from orbital photographs and maintaining constant communication with mission control, which tracked their position using radio signals. A solo walker could not count on continuous communication. The lunar surface would block signals whenever mountains or crater rims intervened. On the far side of the moon, where the Apollo missions never landed, there is no line-of-sight communication with Earth at all. NASA's Lunar Reconnaissance Orbiter has mapped the moon's surface at resolutions as fine as 50 centimeters per pixel in some areas. But these maps exist in computer databases on Earth. A walker would need to carry detailed maps of their entire route, thousands of kilometers of terrain, and be able to correlate those maps with what they actually see. This is harder than it sounds. Without atmospheric haze, everything on the moon appears sharp and clear regardless of distance. There are no familiar objects to provide scale. A boulder that looks like it is 100 meters away might actually be a mountain 10 kilometers distant. A crater that appears shallow might have walls that plunge for hundreds of meters. Several Apollo astronauts commented on this disorienting effect. Armstrong noted that the horizon on the moon is quite close compared to Earth, but distances beyond it are almost impossible to judge. Aldrin described the challenge of navigating terrain that varies a good bit relative to your ability to move over it. A walker crossing the moon would need to develop new intuitions about distance and scale, intuitions that humans do not naturally possess. They would need to learn to read a landscape that has no trees, no buildings, no familiar objects of known size. They would need to do this while wearing a helmet that limits peripheral vision and creates its own optical distortions. And they would need to do it while exhausted, dehydrated, irradiated, and slowly suffocating in the stale air of a suit that has been worn for days or weeks on end. Let us, for a moment, embrace optimism. Let us imagine a future lunar walker equipped with the most advanced spacesuit technology NASA and its commercial partners can devise. The history of spacesuit development is a history of compromise. Every improvement in one area, mobility, life support duration, thermal protection, dust resistance, comes at a cost in another. Making suits more flexible often makes them heavier or more vulnerable to damage. Extending life support duration requires bigger, heavier backpacks. Improving dust resistance may reduce flexibility. The Apollo suits were designed when we knew almost nothing about what lunar surface operations would require. Engineers at the International Latex Corporation, the company that manufactured the suits, worked from theoretical requirements and best guesses. The suits that resulted were engineering marvels, but they were not optimized for walking. The A7L suit worn by Armstrong and Aldrin during Apollo 11 consisted of approximately 21 layers of materials. From the skin outward, a lightweight nylon comfort layer, a neoprene-coated nylon pressure bladder to contain the oxygen atmosphere, a nylon restraint layer to prevent the suit from ballooning under pressure, 5 layers of aluminized mylar interwoven with 4 layers of Dacron for thermal insulation, 2 layers of Kapton for additional heat protection, and an outer layer of Teflon-coated cloth to resist abrasion and fire. All of these layers had to be sealed at every seam, every joint, every opening. The pressure differential between inside and outside the suit, about 0.27 atmospheres, meant that any flaw in the ceiling would cause a slow leak. A major breach would cause rapid death. The suits worked. They kept their occupants alive for hours on an airless world. But they were stiff, unwieldy, and exhausting to wear. Armstrong himself provided specific feedback after Apollo 11. We should clear that suit so that you could go down to your knees, and we should work more on being able to do things on the surface with your hands. The A7LB suits used on the final Apollo missions, 15, 16, and 17, incorporated some improvements. A waist convolute allowed astronauts to bend at the waist enough to sit in the lunar rover. A neck ring improved visibility, but the fundamental limitations remained. Now, 50 years later, a new generation of suits is being developed. The Axiom Extravehicular Mobility Unit, the AXMU, represents a significant leap forward from Apollo-era suits. It incorporates bearings at the shoulders, waist, and hips that allow something approaching normal walking. You will not see the bunny hopping and falls like those seen in the Apollo videos, said Marshall Smith, director of NASA's Human Lunar Exploration Program, because we have added bearings and new soft elements to help the suit move smoothly with the wearer. The XEMU design, upon which the AXEMU is based, is meant to let astronauts walk and even kneel on the lunar surface. It can be custom-fitted to astronauts of various sizes. It has improved dust mitigation and enhanced life support systems. If such a suit could achieve the 5 km/h walking speed that NASA's 2014 study suggested was possible with improved flexibility, our theoretical crossing time drops to about 91 days. But 91 days is still 3 months, and the moon remains the moon. Even with a perfect suit, you would still face the temperature extremes. You would still accumulate radiation. You would still breathe recycled air, drink recycled water, and consume carefully rationed food that must be delivered somehow to a moving target on an alien world. The human body is not designed for 3 months of continuous walking even on Earth. Ultramarathon runners and long-distance hikers can attest to the toll that extended locomotion takes. Studies of 100-kilometer walking events found that participants who completed the distance in about 24 hours averaged a speed of just 4.12 kilometers per hour, and they were walking on flat, groomed surfaces with access to food, water, and rest stations. On the moon, with reduced gravity interfering with normal muscle loading, bone stress, and cardiovascular function, 3 months of walking would cause physiological damage that we cannot fully predict. Muscle atrophy, bone loss, cardiovascular deconditioning. The body adapts to reduced gravity, and those adaptations are not helpful for walking. This is one of the most insidious challenges of extended lunar operations. On Earth, every step you take loads your bones and muscles. This loading is a signal that tells your body to maintain bone density and muscle mass. Remove the loading, as happens in the weightlessness of orbital spaceflight, and the body begins to shed bone and muscle. Astronauts on the International Space Station lose about 1 to 2% of their bone mass per month. Despite rigorous exercise programs, muscle loss is even faster. After 6 months in microgravity, astronauts may have lost 10 to 20% of their muscle mass and bone density. The Moon's 1/6 gravity is not zero gravity. There is some loading, some stimulus for bone and muscle maintenance, but it is far less than Earth normal. A person who weighs 70 kilograms on Earth weighs less than 12 kilograms on the Moon. Every step applies only 1/6 the mechanical stress. Over a 7-month lunar traverse, a walker would experience progressive deconditioning. Their bones would slowly thin, their muscles would weaken, their cardiovascular system would adapt to the reduced demands of low-gravity locomotion, becoming less efficient at pumping blood against Earth normal gravity. By the time the walk was complete, if it could be completed, the walker might be too weak to return to Earth. Astronauts returning from 6-month ISS missions require weeks of rehabilitation before they can function normally in Earth's gravity. A walker returning from 7 months on the Moon, having experienced far less loading than ISS astronauts get through their exercise programs, might require months of rehabilitation, if they could walk at all. This is the cruel irony of lunar exploration. The very act of spending time on the Moon degrades your ability to survive returning from it. The Apollo astronauts who spent the most time on the lunar surface, Cernan and Schmidt, during Apollo 17, were there for about 75 hours total, with just over 22 hours of EVA time across 3 excursions. They drove the lunar rover for 35.7 kilometers. They walked far less. And when they returned to Earth, they had already begun to show the effects of their brief exposure to reduced gravity, despite intensive exercise and the short duration of their mission. So let us finally answer the question: how long would it take to walk across the Moon? If you are asking about the theoretical minimum, a human in a perfect suit walking at 5 kilometers per hour with unlimited life support, the answer is about 91 days. If you are asking about what Apollo astronauts could actually achieve with their suits and equipment, the answer is closer to 207 days. And that is if they could walk continuously, which they could not. If you are asking about what is realistically possible with current technology, given the need for rest, shelter from temperature extremes, radiation protection, suit maintenance, and resupply, the answer is that we do not know. It might take years. It might be impossible. The longest continuous walking event in Earth's history is the Mammoth March, a 100-kilometer hiking event in which participants walk for about 24 hours. The average completion speed is about 4.12 kilometers per hour. Extrapolating from this, a truly exceptional walker on Earth might be able to cover about 35 to 50 kilometers per day, sustained over an extended period. On the Moon, with lower gravity, awkward suits, difficult terrain, and the need for regular rest in pressurized shelters, a sustainable pace might be closer to 15 to 25 kilometers per day. At that rate, crossing the Moon's circumference would take 437 to 728 days. That is over a year, possibly 2 years, on a world where the longest human presence has been 75 hours. But here is what makes this question truly profound. The Moon is right there. You can see it tonight, if the sky is clear. It looks close enough to touch. Children point at it, and ask if they can visit. And yet, for all our technological advancement, for all our rockets and rovers and robots, we cannot simply walk across it. The moon is a 3-day journey by spacecraft. It is perhaps a 2-year journey on foot. And those two facts, sitting side by side, reveal something essential about the nature of space exploration. Space is not just far. It is hostile. Every meter of progress must be fought for against an environment that does not care whether you live or die. The distances that seem trivial on a map become vast when measured in human breath, human heartbeat, human endurance. When Neil Armstrong and Buzz Aldrin walked on the moon in 1969, they traveled a total of about 250 meters, less than the length of 3 football fields. That was enough to change human history forever. When the Artemis astronauts return to the moon in the coming years, they will have better suits, better technology, better knowledge. They will walk farther than Armstrong and Aldrin. They will stay longer. But they will still be constrained by the same fundamental reality. The moon is a world designed to kill you. And yet we go anyway. We go because the moon is there. Because the question of what lies over the next crater rim, the next mountain range, the next horizon is encoded in our DNA. We have been walking to new places since before we were fully human, and we will not stop now. Perhaps the most haunting aspect of this question is not the answer, but what the answer reveals about our relationship with the cosmos. We are fragile. We evolved in a thin envelope of air wrapped around a warm, wet rock. Take us outside that envelope, and we die, quickly, painfully. The moon is not far away in cosmic terms. Light reaches it in about 1.3 seconds. But it is far enough away to require extraordinary measures just to survive there for hours. And yet, 12 human beings have walked on its surface. They left footprints that will last for millions of years, untouched by wind or rain. They looked back at Earth and saw it as a fragile blue marble suspended in infinite darkness. They came home changed. Eugene Cernan, the last human to stand on the moon, described his final moments on the surface in December 1972. As he climbed back into the lunar module, knowing that no one would follow for decades, he looked out at the stark grey plains and said goodbye. 50 years later, we are preparing to return. The Artemis program aims to put the first woman and the next man on the lunar surface within the next few years. This time, we plan to stay, to build bases, to learn how to live on another world. But we will still be walking slowly. We will still be fighting against suits that do not bend right, dust that invades everything, temperatures that swing from hell to frozen hell. We will still be measuring our progress in meters, while dreamers on Earth talk about circumnavigation. That is the real answer to the question. How long would it take to walk across the moon? Long enough to force you to reckon with what you are. A soft, water-based organism with about 90 minutes of oxygen, trying to cross a world that has been silent and dead for 4 billion years. Long enough to remind you that the universe is not built for humans. We built ourselves for it, piece by piece, step by step, lifetime by lifetime. And then there is the radiation. We have mentioned it briefly, but it deserves deeper examination, because radiation is perhaps the most insidious danger of all, invisible, odorless, undetectable by human senses, accumulating silently in your tissues with every passing hour. The moon has no magnetic field to speak of. Earth's magnetic field deflects the vast majority of charged particles from the sun and deep space channeling them toward the poles where they create the aurora. The moon has no such protection. It is naked beneath the cosmic bombardment. Two types of radiation concern lunar explorers. The first is solar particle events, bursts of protons and other charged particles ejected by solar flares and coronal mass ejections. These events are unpredictable, but can be extremely intense. The solar storm of August 1972, which occurred between the Apollo 16 and 17 missions, would have delivered a potentially lethal dose to any astronaut on the lunar surface. The second type is galactic cosmic radiation, high-energy particles that originate outside the solar system, accelerated to enormous velocities by supernova explosions and other cataclysmic events. GCR is constant and cannot be avoided. It includes protons, helium nuclei, and heavy ions that can penetrate meters of shielding. The Chang'e 4 lander's measurements, published in Science Advances in 2020, found that astronauts on the lunar surface would receive about 60 microsieverts of radiation per hour. That translates to about 1.44 millisieverts per day, roughly equivalent to receiving 1.4 chest X-rays every day. Over a 7-month traverse, 210 days, the cumulative dose would be approximately 300 millisieverts. For comparison, the average annual radiation dose for a person on Earth is about 2.4 millisieverts. A lunar walker would receive 125 times their annual Earth dose in 7 months. This level of exposure significantly increases lifetime cancer risk. NASA limits astronaut career radiation exposure to levels calculated to keep the excess cancer mortality risk below 3%. A 300 millisievert dose from a single lunar traverse would consume a substantial fraction of a typical astronaut's career limit. And that assumes no solar particle events occur during the journey. But the chronic effects are not the only concern. Solar particle events can deliver acute doses that cause immediate symptoms: nausea, vomiting, fatigue, depressed immune function. A major event could be incapacitating or fatal within hours. A lunar walker would need to have access to shelter, heavily shielded structures where they could take refuge during solar storms. Spacecraft walls and spacesuit materials provide some protection against solar particles, but not enough for a major event. Calculations suggest that about 2 meters of lunar regolith would reduce solar particle radiation to acceptable levels. This is why lunar-based concepts often envision underground habitats. But a walker in transit across the lunar surface has no underground shelter. They would need to carry or have access to portable shielding, adding yet more mass to an already impossible logistical burden. Or they would need to accept the risk, to walk knowing that at any moment the sun could erupt and kill them before they could take cover. This is the reality of lunar exploration. Not the sanitized adventure of science fiction, but a constant negotiation with death. Long enough that by the time you reach the other side, if you reached it, you would not be the same person who started. And perhaps that is the point. The moon does not exist to be walked across. It exists to teach us what we are capable of becoming. Consider the psychological dimension of such a journey. We have focused on the physical challenges, the suits, the dust, the radiation, the terrain. But the mind is as vulnerable as the body. 7 months alone on the moon, even with radio contact to Earth, which would not be continuous. The loneliness would be profound. On Earth, we are surrounded by life, birds, insects, plants, other people, the constant hum of civilization, the knowledge that help is nearby if we need it. On the moon, there is only silence. The absence of sound is not like a quiet room. It is the absolute silence of a world with no air to carry vibrations. You would hear only your own breathing, your own heartbeat, the mechanical noises of your suit. Nothing else. For 7 months. The landscape offers no comfort. Earth environments evolved alongside human consciousness. We find forests and grasslands and shorelines beautiful because our ancestors survived in them. The neural circuits that respond to natural beauty are tuned to terrestrial environments. The moon is not natural in this sense. It is a world of grey on grey, punctuated by black shadows and white highlights. There are no curves that suggest life, no colours that evoke Earth. Studies of lunar photographs consistently find that people describe the moonscape as desolate, barren, dead. These are not just descriptions. They are emotional responses to a world that offers nothing our psychology evolved to recognize as home. Apollo astronauts described powerful emotional reactions to their time on the moon. Some spoke of transcendent awe at seeing Earth hanging in the black sky, a fragile blue marble in infinite darkness. Others felt an urgent desire to return, a sense that the moon was fundamentally wrong in ways they could not articulate. Edgar Mitchell, lunar module pilot of Apollo 14, experienced what he called a profound sense of universal connectedness while returning from the moon, an experience that led him to spend the rest of his life studying consciousness and spirituality. Charlie Duke, lunar module pilot of Apollo 16, became a born-again Christian after his mission, seeking meaning in the face of an experience that defied ordinary meaning. A solo walker spending 7 months on the moon would undergo psychological changes we cannot predict. The isolation, the sensory deprivation, the constant stress of survival. These would reshape the human mind in ways that have never been tested. Some might find clarity and peace in the absolute solitude. Others might lose their grip on reality, hallucinating companions, conversations, environments that exist only in their deteriorating minds. There is no psychological research on 7-month solo lunar expeditions because no one has ever done anything remotely similar. The closest analogues are polar expeditions, solo ocean crossings, and long-duration solitary confinement. The research on these experiences suggests that some people thrive in extreme isolation, while others suffer permanent psychological damage. There is no reliable way to predict in advance which category any individual will fall into. A lunar walker would be making a wager with their own sanity. There is a plaque on the moon left behind by the Apollo 11 astronauts in 1969. It reads, "Here men from the planet Earth first set foot upon the moon. July 1969, AD. We came in peace for all mankind." 55 years later, those footprints remain. The dust has not been blown away. The plaque has not corroded. Nothing changes on the moon. Time passes differently there, marked only by the slow radiation damage to abandoned equipment and the occasional micrometeorite impact. If you walked across the moon, you would pass through a landscape frozen in time. You would see the tracks left by lunar rovers, the descent stages of lunar modules, the flags that may or may not still have their colors after decades of solar bleaching. You would walk through history. You would also walk alone. There is no sound on the moon except your own breathing, your own heartbeat, the creak of your suit. No birds, no wind, no distant traffic. Just silence so complete it becomes a presence, pressing against you from all sides. Astronauts have described looking up at the stars from the lunar surface and seeing them as points of unwinking light, steady and eternal, undimmed by any atmosphere. The sky is black even when the sun is shining. You could walk for months and never see a sunrise in the way you understand sunrise. Just a slow brightening along one horizon as the sun creeps up over 2 weeks. This is what it would mean to walk across the moon. It would mean walking through a world that is not made for you, that does not acknowledge your existence, that will be exactly the same whether you cross it or not. It would mean understanding in your bones, in your muscles, in every struggling breath, that the universe is vast beyond comprehension, and that you, against all odds, are here, moving through it, one step at a time. The answer, in the end, is not a number. It is a meditation on human limitation and human aspiration. It would take approximately 91 days to walk across the moon under ideal theoretical conditions. It would take 207 days or more with Apollo-era technology. It might take 1 to 2 years with realistic constraints on rest, resupply, and survival. But the real answer is that it would take everything we have, every ounce of engineering brilliance, every calorie of human determination, every moment of our short and precious lives. And still, it might not be enough, but we will try anyway, because that is what we do. We walk toward the horizon, even when the horizon is airless and cold and 10,117 kilometers around. We take one step, then another, then another. This impulse to explore is not rational. Rational beings would stay home, comfortable and safe, living out their lives within the narrow band of conditions that support human existence. Rational beings would not strap themselves to towers of explosive fuel and hurl themselves into vacuum. But humans are not purely rational beings. We are dreamers, strivers, explorers. We crossed the African savanna when it would have been safer to stay in the trees. We spread across every continent, adapting to jungles and deserts and frozen tundra. We crossed oceans in vessels that had no business surviving the voyage. We climbed mountains for no reason other than that they were there. The moon is the next step in this ancient progression. Not because we need to go. There are no resources on the moon that we cannot find more easily elsewhere. No land to settle that could not be created more cheaply on Earth. We go because looking up at that pale circle in the night sky and knowing that humans have walked there is different from looking up and knowing that we could walk there, but chose not to. The difference matters. It shapes who we are as a species. The 12 humans who have walked on the moon did not go there as individuals. They went as representatives of humanity, carrying with them the accumulated dreams and efforts of billions of people. When Armstrong stepped onto the surface and declared it a giant leap for mankind, he was not exaggerating. It was a leap that changed our species' conception of itself. Before Apollo, space was the realm of gods and science fiction. After Apollo, space became a place where humans could actually go with sufficient technology, sufficient resources, sufficient will. The psychological barrier had been broken. The impossible had been proven possible. But 50 years have passed since the last Apollo mission. The humans who walked on the moon are elderly or dead. For most people alive today, the moon landings are history, as remote and abstract as the voyages of Columbus or Magellan. The living memory of lunar exploration is fading. The Artemis program aims to change that, to put new boots on lunar soil, to create new memories, new footage, new voices describing what it feels like to walk on another world. This time, NASA says, we are going to stay. Not just to visit, but to learn how to live. This is the real significance of asking how long it would take to walk across the moon. Not because anyone is planning to do it in the near future, not because it is a practical goal, but because asking the question forces us to confront the reality of what lunar exploration actually involves. It is easy to look at the moon and imagine gliding effortlessly across its surface, bouncing like the astronauts in the old footage. The reality is harder, slower, more dangerous, more demanding of courage and endurance and will. And that is exactly why it matters. We walk, and eventually, against all odds, we arrive. That is the promise of the moon. Not that crossing it will be easy, not that it will be fast, not that it will be safe, not that you will return unchanged or return at all. Only that it is possible that if you are brave enough, stubborn enough, determined enough to take that first step, and then the next, and then the 10 billion steps after that, you could walk across another world. Only that it is possible, and that makes all the difference. So the next time you look up at the moon, ask yourself, how far could you walk before you gave up? How far could you push your body, your mind, your will, before you decided it was too much? The moon does not answer. It never does. It just waits, patient, silent, watching to see if you will take the next step.